Hello, my name is Kiril Griazev. I'm from Vilnius Gediminas Technical University, located in Vilnius, Lithuania. And today I would like to present to you a new approach that can be used for sibling block detection that can help to simplify web page content labeling process. A key challenge during web segmentation is the necessity to detect and associate similar content that may be dispersed across different parts of the same page. This is crucial to decrease the workload required for content labeling and also to reduce the computational demand during the content analysis. And because some portions of similar content can be excluded from processing. There are various techniques for related block detection, but generally you need to combine multiple methods in order to achieve the best results. During our approach, we used document object model tree traversal, CSS selector matching, textual similarity, and heuristic approaches. In order to link related content presented on the web page, we perform multiple optimization steps. This section will cover some key optimization steps from our previous research that we reuse during remote siblings detection. HTML code has a hierarchical structure where one tag contains other tags that define smaller components. But quite often, content may have additional tags present that are used in order to achieve desired visual layout and do not provide any additional data. These additional blocks represent different length variations of the same content block because the content itself does not change. In the presented image, you can see how we define two types of boundaries for each content block: maximum boundary and minimum boundary. These boundaries signify the limits within content of the block stays the same. Another optimization we do is detection of direct siblings. These are blocks that follow a similar structure and have the same parent. When such blocks are encountered, we only need one of them for further processing, while others can be discarded and connected to the selected block via relationship. This allows us to further reduce the number of content blocks, and each sibling also gets optimized for minimum and maximum boundary. During the direct siblings detection process, we evaluate the similarity score of processed blocks. Basically, we compare the structure of the blocks. During our research, we received the best results when similarity threshold was set at 0.92, and this way we receive very little, only a few false positives from time to time. Later on, we use this data for remote siblings detection. Now, to validate our initial results, we used two datasets. One was constructed by us, while the other was an open source. Open source dataset was selected because it was used in multiple research papers that we have read. The main difference between these datasets is that our dataset is way more detailed, averaging 91 labeled blocks per website, while open source averages only 16 blocks per website. We were able to increase the ratio of user-labeled blocks versus the number of content blocks extracted from the website from 7 to 24%. This is the increase for the dataset that we created. For open source dataset, increase was from 3% to 11%. The benefit of this increase is that in case of manual labeling, the labeling effort is being reduced because the total number of content blocks is lower. Discarded blocks are auto-labeled thanks to the relationship they have with blocks that are selected for further processing. Now we will present our proposed remote siblings optimization step. Remote siblings are very similar to regular siblings we just discussed. They also represent blocks that have a similar structure, but in this case, they have a different parent. In this example, you can see content blocks marked with red squares. Each of the content blocks groups represents a group of direct siblings. So we would have two groups of direct siblings without remote sibling detection. We display the relationship, the connection of these direct siblings by using a yellow arrow. So after we implement remote siblings detection, we can connect these groups together. And we represent this by a green arrow. So let's compare an example of two sections that have multiple sibling blocks. In this case, different card layouts prevents these sections from being meshed as similar blocks. So we need to analyze the content of each section and try to extract similar data from them. We can see two distinct card layouts in both sections. These are marked by different colors. Solid border blocks in this example represent blocks that are selected for further processing, while dashed border blocks will be discarded and a relationship will be created to the selected blocks. As a result, with only direct sibling detection, we will proceed with 4 blocks and 5 blocks will be discarded. Now, if we apply remote siblings to the same blocks, we can further reduce the number of blocks and only select blocks number 1 and 2, and blocks 5 and 6 are also getting discarded. So with remote siblings, we analyze both of these card sections as one, and this allows us to select only 2 blocks instead of 9 for further processing. Now, here's an overview of the same situation. So not only we are able to remove direct and remote siblings, we can also discard any additional content that they contain. So as we talked before, HTML is a hierarchical structure where one block may contain other blocks. Now, because these blocks are deemed to be similar, we can say that their contents must be similar as well. So all of the inner blocks are also being discarded. Now, in order to perform remote sibling detection, we need to compare 2 content blocks. We do this by comparing the structure. To simplify and speed up the process of comparison, we adapted a new tree notation to our needs. Tree generation is being performed in 2 steps. First, we generate initial tree, then we optimize it by discarding empty nodes. Out of 2 types of trees that we generate, we will discuss the details of each type in the following slides. So after we have the trees, we search for matches in the dataset and link matching blocks together. Once again, only matching block is kept and other blocks are discarded after we create a relationship. So here you can see one of the types of the trees we generate. We will use the simple HTML section that contains a header and navigation menu to basically present you an example of a generated tree. So loose tree consists of tags only. During initial tree generation, we do not check whether node has any children, thus empty nodes may occur. That's why we perform a second step of optimization, and currently in this step, we remove these empty nodes, keeping only tag information. Now, a part of the loose tree, we also generate a strict tree. Strict, in this case, strict tree allows us to perform a stricter comparison, because now we also include the class data of the tag. Optimization in this case is the same as before, and we remove empty nodes. If there is a need, we can add any other metadata from the tag to the tree, not only class data as we do now. So after implementing the remote siblings detection, we were able to further increase the ratio of user-labeled blocks versus extracted content blocks. Once again, the benefit of increase here is that in case of manual labeling, the labeling effort is being reduced because the total number of content blocks is lower, so the users need to label less blocks. Discarded blocks are auto-labeled thanks to the relationship they have with blocks that are selected for further processing. Open source dataset improvement was not as high in this case as with our own dataset, but this is partly due to the fact that websites in 2013 were simpler and there was less usage of repeatable components. During testing, we discovered that our current approach has some limitations. It is not suitable for content blocks that consist of 3 or less tags. We get way too many false positive cases with such blocks. This is somewhat mitigated by using strict trees, but still requires additional fine-tuning. Due to a similarity threshold of 0.92, there is a chance that a small amount of data can be lost. We currently do not check for that data, but it is possible to recover it by additional processing for blocks that don't have a 100% match score. Overall, we were able to reduce the extracted content blocks so that user-labeled blocks accounted for 47%. Without optimizations, this ratio was at 7%, which results in vastly smaller effort during block labeling process. We were able to reduce total number of content blocks by 83%, meaning that only 17% of content blocks needs to be manually labeled, and the rest can be auto-labeled or discarded as not usable content. By implementing remote siblings detection, we improved the reduction ratio by 50% when compared to our previous optimization method. Some limitations were discovered, potential solutions were suggested, and these suggested solutions would allow us to further reduce the number of content blocks that need to be labeled. In the end, this all results in way smaller effort for manual labeling when we need this data, for example, for machine learning. And thank you for your attention.